Hi students, hope everyone is fine and safe. It gives me immense pleasure to welcome you all to my new video, and today's video is about another interesting topic in Unit 4. We're going to see performance of pipelining, right? We've already seen what is the basic concepts of pipelining, right? And today we're going to see performance of pipelining concept, okay? And before watching this video, it is very important you got to understand what is pipelining, what is two-stage pipelining, what is four-stage pipelining, right? So if you have not watched the previous video, please go and watch the basic concept of pipelining and then come to this video so that you can understand the concept very clearly, right? So before starting with the pipelining performance, right, you got to understand why pipelining is very, very important for the processor, right? If you take any particular CPU, right, you can look at this particular diagram, right? If there is no pipelining, right, if it is not a pipelining processor, you can see here at the end of the fourth clock cycle, what will happen? This is instruction 1 and this is instruction 2, right? Till 4th clock cycle, it will execute only one instruction, fetch and then decode and then execute, then write and then clock, right? That is 4 execution, right? Fetch, decode, execute and write, correct? Right. So only after the 4th stage, right, it will go to the next, right? It will go to the next instruction. This is called sequential execution, correct? Right. So if you take at the end of the 4th clock cycle, it will be performing only, it will have executed only one particular instruction, right? But if it is a pipelined processor, right? If it is a pipelined processor, what will happen? You can see here at the end of the 4th cycle, right? You can see instruction 1 is completed all the 4 stages, right? And instruction 2 completed 3 stages of execution, right? So this is very, very important, right? And that is why pipelining is important for the processor, right? Because what will happen here, the pipelining, it will not execute the instruction, it will not make the single instruction to execute faster. But what will happen here is it will improve the throughput of the processor. It will improve the throughput, that is number of instructions that is executed at per unit time. Like you can see here at the end of the 4th clock cycle, here only one instruction is executed, but here 2 instructions is almost completed here, right? That is the main performance of pipelining. Why is that we go for pipelining is to improve the throughput, to increase the rate of operation, that is the complete instruction, right? The number of instructions that is executed per unit time will be more, right? And the time taken to execute the instruction, the list of instructions will be very, very less if you use pipelining, right? That is very important for understanding the pipelining performance, right? As I said, pipelining increases the CPU throughput, right? The number of instructions that is executed per unit time, right? Which is also reduces the time that is taken for number of instructions, correct? And for example, if you take a normal processor, right, which performs sequential operation, right? A pipeline processor will be 4 times greater, 4 times faster when compared to the processor which is not pipelined, right? And the number of performance, that is the number of stages is related to the performance of the processor, right? That is directly related to the performance of the processor, right? If the number of stages increases, then the performance will be more, right? And one thing is very, very important. We know that there will be 4 cycles, that is fetch, decode, execute, and as well as write, correct? Right, and all the stages has to be completed within a particular clock period, right? And the pipelining concept will be very effective only if all the stages complete this operation within the clock period, within the given time, right? If any interruption takes place, right? If any interruption, for example, if this decode phase is not completed within the particular time, or if this execution is not completed within the particular time, right? Then what will happen is the whole pipelining operation will be stopped. It will be halt. It will be stalled. Okay, it will be calling us stalling the pipelining operation, right? It will hold the complete pipelining operation, right? right? And we should not have any such interruption, right? And that interruption, right, which is stalling the pipelining operation is called as Assads. It's called as Assads. And it is very important that, right, we should be very sure that there is no interruption when the pipelining process is going on, right? There should not be any hazards. Even if there is any hazards, that has to be limited, right? That has to be overcome. Only then the performance of the processor will be very good, right? Now you understand what is pipelining performance is all about, right? It is all about increasing the throughput, right? And very importantly, the performance of pipelining will be degraded if there is a hazard, if there is any interruption, right? And when you speak about hazard, there will be different types of hazards, okay? There will be 3 different types of hazards, right? First, you have to understand what are the 3 different types of hazards, okay? That is data hazard. Data hazard. We will see hazards very detailed in next video, right? Here, just we are seeing what is hazard and how it is affecting the performance of the processor, right? The pipelining, right? So there is 3 hazards. One is data hazard, another one is control hazard or instruction hazard, and then one is structural hazard. Next one is structural hazard. Okay, right. So now this is an example for data hazard, right? We know that fetch for every clock cycle, right? You know that from this diagram you understand that at the first clock cycle, instruction fetching of first instruction will start, and at the second clock cycle, decoding of first instruction will start and fetching of second instruction will start, and at the third stage, like that it goes on. You know that, correct? Right. And it is assumed that each and every processor, each and every stage has to perform, each and every hardware unit, a fetch unit, decode unit, execute unit has to perform its operation within that particular time period, right? You know that in execution phase is the where you will perform all the exact operation, right? It is the one which performs all the arithmetic and logic operation. It will perform the arithmetic and logic operation, right? And most of the operation will be completed within the given time period, right? For example, if you take addition, subtraction, all those are very simple, right? Addition is very, very simple arithmetic operation, right? It will be executed very fast, okay? But if you take division, right? If you take division, it will take more time, right? It is little complex than addition, right? Sometimes it will be more complex that it will not be able to complete that particular operation within the given clock period. You can see here while executing the second instruction, right? You can see the first instruction completes everything, fetch, decode, execute and write within the given time period, correct? But you can see the second instruction, right? The execution unit of the second instruction starts at the 4th cycle but ends only at the 6th cycle, right? Instead of completing within 1 clock cycle, it takes 3 clock cycles here, right? It takes 3 clock cycles here. Maybe it may be a division operation, okay? So it takes 3 clock cycles, which means, right? Which means that it is expected to complete at the end of the 4th clock cycle, but it is completing only at the 6th clock cycle, right? So what happens here, it not only takes more time, it also halts the write operation, right? It makes the write operation to wait for 2 clock cycles, right? And also it will further stops the execution of other instructions as well. You can see here, right? The instruction 3 execution will be stopped for 2 clock cycles, right? The execution will not start, right? Similarly, the decode of the 4th instruction will not be started, correct? It has to wait for 2 clock cycles, right? So if one particular interruption will if happen, then it will completely halt the complete pipelining operation. Okay. Not only here, you can see here, it not only halts this particular writing operation, right? It will also halt the first stage and the second stage. That is, it will not get the new instruction. The fetch instruction will not be able to get the new instruction, right? And the decode instruction will not be able to decode the next instruction because all the operations will be completely halted here, right? And this is called data hazard. That is because, right, why is that we are calling this data hazard? because only after completing the execution phase, right? What is write phase? Write phase is the one which will write the result in the destination, correct? Right. So it needs a data. It needs a data. For example, the same information at R1, R2, correct? And it has to save the result in R2, right? It knows that I have to know. It knows that it has to save the information in R2, but it has to get the data from the execution unit. Only then it can able to save the data in the exact location, right? So here the data is not reached at the correct time, right? And because of that, the complete operation is stopped, and that is why it is called as data hazard, right? Hope you understand, right? So if you understand the concept clearly, you can write it by in your own words, right? So this is called as data hazard. Similarly, there are various different reasons which will halt or which will interrupt the pipelining process, right? And one thing you have to be very sure here, right? This pipelining stage, right? It not only happens because of data, it also happens for other reasons as well. For example, the second one is instruction hazards, right? What is instruction hazard? It can be also called as control hazard. It can be also called as control hazard. Okay, right? We already know that there is something called cache memory, right? Why is that we use for cache memory? Right, I already said in previous video what is the importance of cache memory. If there is no cache memory, right, what will happen? The instruction has to be fetched from the main memory, which will take more time. Correct? Right. Now you can see here, this instruction hazard is nothing but, right, getting the information itself becomes late. Right? Here what happens? Data hazard. Getting the data becomes delay, then that is called as data hazard, right? If fetching the instruction itself becomes delayed, getting the instruction itself getting delayed, then that is called as instruction hazard, right? For example, right, we know that there is a cache memory, right? And if the cache memory does not have that information, or if the cache misses to fetch that particular instruction, what will happen? The processor has to get that information from the main memory, correct? You can see here, this is processor, and this is cache, and this is main memory. And the processor, what it will do, it will get all the information from cache itself. So it will take only lesser time. If the cache misses the instruction, or if the instruction is not in the cache, then the processor has to go to this main memory and get the information and reach the processor again. Right? So it will take more time. Right? And because of that, the interruption will happen in the pipelining. That is called as instruction hazard. You can see here instruction 1, there is no problem, right? It fetches, decodes, executes, and writes and completes it in 4 clock cycles. Okay, and you can see instruction 2, fetch starts at the 2nd clock cycle, but the cache does not have that information, or it misses that particular instruction. So it has to get the information from the main memory, correct? Right, so you can see here the fetching this instruction, it takes here 3 clock cycles, right? You can see here it takes even 4 clock cycles here, right? Normally it has to be completed at the 2nd clock cycle, but it takes 5 clock cycles to complete, right? That is 2, 3, 4, 5, right? It takes totally 4 clock cycles to complete the fetch phase itself. Right, and because of that, what will happen, right, the decode phase will start only at the 6th cycle, and instruction fetch 3 will happen only at the 6th cycle, right? And this is called as instruction hazard, right? And you can see till this no operation will take place, correct? Right, this is called as instruction hazard, or it can be also called as control hazards, right? And there is one final hazard which is called as structural hazard, right? We know what is data hazard and what is instruction hazard now, right? And in the instruction hazard, you can see here, right, this is one concept which I have explained. We can also represent the same concept like this one, right? The representation of the pipeline. You can see here, right, at the 2nd phase, right, you can see here, instruction 1, right, it starts at the 1st cycle, right? 2nd, 3rd, and 4th, it completes at the 4th cycle. The complete execution is completed, right? But if you take instruction 2, what happens? The fetch phase is completed only at the 5th clock cycle, right? So because of that, what happens here? The decode phase is idle for third clock cycle, fourth clock cycle, and fifth clock cycle. 3, 4, 5. Right? It is idle for 3, 4, 5 clock cycles. And similarly, the execution unit is idle for 4, 5, 6 clock cycles. You can see here 4, 5, 6. Similarly, the right unit is idle for 5, 6, 7. Correct? Right. And one thing I have to say, this is called as stalling. I have to say this is called as stalling the pipelining operation. Right? And we can also say that as Assard. Right? And we can also say it as bubble. We can say it as a bubble. Right? We can call it as bubble. That is, once the bubble is created here, right? And it will move to the next stage and it will go to the next stage. Like that, it will go to the end, right? Once the bubble is created, it will move to the next stage until the next last unit, that bubble will move forward, right? Right. So this is very important in pipelining, right? And the Assads, right? We have to make it very sure there should not be any interruption, there should not be any hazards in pipelining. Only then the performance will be good. Correct? So this is about instruction hazards. Okay? And we'll see about structural hazards. Okay? So this is complete theory, right? But you got to understand what is structural hazards. Okay? So what is structural hazards? Right? So what is structural hazards? So far we have seen what is data hazard and what is instruction hazard, right? If the data is delayed, then it is called data hazard, and if the instruction fetching is delayed, then it is called as instruction hazard, right? And what is structural hazard? If two instructions, right? If two instructions needs to execute or needs to access the same hardware unit at the same time, then it will cause hazard in pipelining. It will cause an interruption, right? That particular hazard is called a structural hazard, right? For example, there is one particular register called R2, right? I'll give an example for it, right? And if two instruction has to register, if it has to access this particular register at the same time, right? Then it will cause interruption in the pipelining, right? That is called a structural hazard. A very good example is accessing the memory, right? Accessing the memory, right? We know that, right? The execution unit, the decode unit, what the decode unit will do? It will fetch the operands, right? It will fetch the operands from the memory, right? And you know what is fetch? Fetch unit will do. What fetch unit will do? It will fetch the instruction from the memory, right? So now, if you see that two instruction 1 and instruction 2. For example, if instruction 1, right, if instruction 1 needs to access memory for decode phase, and if instruction 2 has to access memory for fetch phase, right, then there will be an interruption, right? Then only one operation can take place at a time, right? So it will halt the other operation, right? This is called as structural hazard, right? And only one operation can be executed at that particular time, right? And that is what I have explained in this particular theory. Okay, right? And we will see an example for structural hazard. Okay, and you can see here this structural hazard. Okay, this particular instruction load X R1 comma R2, right? And you can see here the instruction 1, right? It fetches, decodes, executes, writes, right? It completes in the 4th clock cycle. Now I2 is this instruction. I2 is this instruction. Okay. Now you can see here at the 2nd clock cycle it will fetch this instruction. Correct? It will fetch this instruction, right? And at the 3rd clock cycle it will decode, right? It will decode that particular instruction, right? And after decoding, the execution will start, correct? And while executing this instruction, you can see here there is something X, R1, R2, correct? We know that we have to move the content of R1 here to R2, right? But there is an offset value here, right? So first what has to do, the execution unit, right? It cannot complete that particular operation within 1 clock cycle. Why? Because it has to first compute x plus r1, right? And then it has to access the memory for r1, correct? Right. So now you can see here the execution unit will take place at through 2 clock cycles, that is at 4 and as well as 5. But normally it has to complete at 4th cycle itself. So at the 4th cycle, what it will do, it will compute x plus r1. And at the 5th cycle, what it will do, it will access the memory, right? And only after accessing, it will write that particular result. It will move that content to the R2, right? That is, it will load the content to the R2, correct? So it will be done at the 6th clock cycle. Okay, so you can see here, right? It halts the pipelining operation. That is, execution take place here, right? Here it takes 2 clock cycles. Okay, and because of that, you can see here, right, the instruction 3, right, the writing phase of the instruction 3 is halted, and similarly the execution of 4th instruction is halted, right? That's because if it is not halted, what will happen here, right, both this instruction I2 and I3 will be accessing the same register R2 at the same time. Okay, right? So to prevent that, what will happen here, right, here it takes 2 clock cycles, so the Assard will happen, that is, an interruption will take place here, right? So there will be an hold here, right, and this particular interruption is called as Assard, and this particular Assard is called as structural Assard, right? And when 2 instructions try to access the same hardware unit, that is where structural Assard will take place. Okay, and when it comes to execution of pipelining, that is, when it comes to the performance of pipelining, you got to understand that you have all these hazards. The pipelining concept is very important, that it does not improve the performance of, or it does not increase the speed of one particular instruction. Rather, what it will do is, it will increase the number of instructions. It increases the throughput, the number of instructions that is executed per unit time, right? And that is why pipelining is very, very important, right? At a given amount of time, number of instructions will be executed more, right? And very importantly, the designer of the processor has to be very, very careful with the hazards, right? There should not be data control or structural hazards, right? It has to be limited so that the performance of the processor will be good, right? And the pipelining performance will be good only if all the operations completed at the given time, right, without any interruption, right? This is what I have to explain for performance of pipelining, right? So today what we have seen is, we have seen the importance of pipelining, right? What is the performance of pipelining, right? How it improves the performance of CPU, right? What are the different types of hazards? That is what we have seen. Okay, hope you understand the concept very clearly. Thank you, students.
Thank you, students. Thank you for watching. கண்டிப்பாக இந்த வீடியோ உங்களுக்கு எல்லாருக்கும் ரொம்ப யூஸ்ஃபுல்லாக இருக்கும்னு நம்புகிறேன். Subscribe Passionate Professor and keep learning. Thank you very much.